graphing. Yesterday we talked about graphing. Well, not even graphing, writing it out. What is going on here? We graphed optimizing problems in which we have restrictions, constraints, and objective function. And I was saying to you that yesterday you wanted to make sure that you go through the question and you set up the constraints, and the objective function first, and then the graphing part should be second nature to you. But I said the problem will be is reading the questions and deciphering how to write the equations out, and that in essence is the whole catch in this. Today, so yesterday we just decided that we were going to just set the problems up, and today we're actually going to look at what is it that we're looking at when we have the questions set up. How do we solve to get your values? So our objective function deals with finding either a maximum or a minimum value of whatever it is that we're looking for. And where do we get the coordinates from that? Well, our coordinates will come from the vertices of what we call the feasible region. And I mentioned that yesterday, that you have a feasible region on the graph that shades and holds true for all of the equations that you graph. So on page 166, they've got a graph in which the restrictions are x is an element of all reals and y is an element of all reals. Your constraints are x plus 3y is less than or equal to 9. X minus y is less than or equal to 3. And x is greater than or equal to negative 3. And then they graph it and get your feasible region. So I'm going to pull that up. I'll put that on the board here so that we can look at it together. And then we'll talk about where our feasible regions are and what they look like. Okay, so the first equation was x plus 3y is, thank you, less than or equal to 9, right? So we have that. Oh, error in the equation. Oh, it should be an error. Oh, that should be a plus. So there is an error there. And go. Okay, so there's the first one, right? The second one was x minus y is less than or equal to 3. So we have that area. And then our final one was x is greater than or equal to negative 3, correct? So what is that line going to look like?
Straight up and down.
Straight up and down, going through which coordinate? Negative 3, that's right. So there you have it. Okay. So again, because of the colors, it looks a lot better on my laptop than it does on there. So we'll just shut this off. Okay, so the feasible region then, we're going to have to, I don't know if we can make that smaller or not. No. We're going to find out all the coordinates that are the boundaries for this feasible region. Okay, so boundary number 1, all right, is right here. Back to this. Okay, so boundary number 1 is right there. And what is that coordinate? 4.5 and it says in your book there. Look in your book. 4.5 and 1.5. Okay. All right. This one up here.
Negative 3 and 4.
Negative 3 and 4. Okay. And then this guy down here.
Negative 3 and negative 6.
Okay. So these two guys are fairly straightforward because what I do is I know that they're going through negative 3, right? Okay, so we have to talk about that too. How do I find out where they intersect at? Well, what's the equation of that first line? It was x plus 3y is less than or equal to 9, correct? Is that the equation for the first one? Okay. So I know that it's intersecting where x is equal to negative 3 here. So I put negative 3 in here. So negative 3, add 3y is equal to 9. Just write it in there. Okay. Okay, because I want to find out where they're equal to each other, these two lines. Add that, and then I divide by, so that gives me 12. 12 divided by 3 is 4. So that gives me the 4 there. So when I'm trying to find out where they equal each other, I have to let the equations equal each other. So this coordinate right here wasn't as easy. So I have x plus 3y is equal to 9. And what's this other line? X minus, what's this?
Minus y is less than or equal to 3.
Is equal to less than or equal to 3, right? So I have that. Okay, so I want to solve this then. So this is how you solve without using a calculator. This is how I solve it. Now remember, we learned 3 methods: elimination, substitution, adding, and subtracting. Okay, so I'm going to subtract these two here. So I'm going to change these signs and add them. That gives me 3y, and y is 4y. 9 subtract 3 is 6. Y is equal to 1.5. So this is, again, this is when you don't have the graph. That's how we find out where those coordinates are equal to each other. So I've got the y value here. Now how do I get the x value if I have the y value?
Plug in the y value.
Plug it in into one of the equations. So that first one was x minus y equals 3, right? So I've got x minus 1.5 is equal to 3. X is equal to 1.5 plus 3, which is 4.5. So that's how I get that. So again, this is a review of grade 10. So you may or may not remember this, but you're going to have to use it. So you better find out if you're struggling with it. When I graph it, I can get it because I can clearly see it. But if I don't graph it properly on actual graph paper, I may not get the actual points, the coordinates. Okay? So now I have 3 coordinates. And these are the 3 coordinates that I'll use in my objective equation. So what's the objective equation? Look in your book.
P equals 2x plus y.
P equals 2x plus y. And now I substitute in this for x, this for y, and solve it. This for x, this for y, and solve it. And this in for x and this in for y, and solve it. And that will give me my maximum or my minimum values. Okay, so let's put negative 3 in here. What's 2 times negative 3? Negative 6 plus 4 is? So this guy's negative 2. 4.5 times 2. 9 plus 1.5? 10.5. Okay. Negative 3 times 2? Negative 6 plus negative 6? So we said it, negative 12. Okay. So which coordinate gives me my maximum value? 4.5 and 1.5. Which one gives me my minimum value? Negative 3 and negative 6. Now if I go inside this shaded region, which I call the feasible region, if I go in there and I take any coordinate out of there, it will fall, when I put it into my objective function, the value will fall between negative 12 and 10.5. But we never really concern ourselves with that. All we're concerned about is finding your maximum and your minimum from your intersection points. Okay? So this is how it differs from yesterday. Yesterday you were just to put down the equation, the constraints, the restrictions, and the objective function. Today we're going to shade, find the feasible region, and solve for it. So we understand what we're doing here? You okay? All right. Now that's 6.5. Well, there's only, excuse me, there's only 3 questions on 6.5. Okay, so that's a beauty. Let's look at example 1 on 6.6 now. So it's on page 168. We have to solve the optimizing problem using linear programming. Well, you're going to use the calculators or the iPads. The following model represents an optimization problem. Determine the maximum solution. So I want the maximum solution. Where does the maximum solution come from? One of the points of intersection, and which equation do I put it into?
The objective.
The objective, right? Okay. So I have the restrictions. The constraints now. Y is less than or equal to 1. We'll try and draw it. First, actually, you know what? No, we won't. Let's do it on here. Okay, so go back to here. Grab this. This will work. Try. It. Words magic. I don't like that other piece of garbage I had before. Okay. All right, edit, clear graphs, delete all graphs. There we go. Okay, so let's look at the equations that we have. So the first equation. The first constraint is y is less than or equal to 1. What's that going to look like?
A straight horizontal line.
Horizontal line. In which way will it be shaded? Above or below that horizontal line? Below. Okay. Great. 2y is greater than or equal to minus 3x plus 2. So I've got 2y greater than or equal to
Negative 3x.
minus 3x.
Plus 2.
Thank you. Good. So I've got that. Okay, so the shaded region, of course, is the combination of the two greens. It's hard to see. It's on the right there. Okay. And then the third constraint is y is
Greater than or equal to.
greater than or equal to
3x minus 8.
No, it's gonna be red. Maybe like blue. Yellow.
Balance.
All right, so we've got our graph here now. Right? What is our objective function?
D equals negative 4x plus 3y.
D equals,
Negative 4x plus 3y.
and we want the maximum value to do this. But we have to use only the values that we have from our graph. So there's equation number, or feasible point number 1. Okay, and what is that?
2 and negative 2.
2 and negative 2. Here's number 2. What is that one? 3 and 1. And then 0 and 1. So we're going to use those 3 coordinates, plug them in, and we solve to get our maximum value. Is that correct?
Yeah.
All right. So I put 0 in here. 0 times negative 4. 0. Plus 3 times 1, which is 3. So there's the first one. 3 in. 3 times negative 4 is? Negative 12 plus 3 is?
Negative 9.
Negative 9. 2 times negative 4 is? Negative 8. Negative 8 plus negative 6 is?
Negative 14.
Negative 14. What is our maximum value?
3.
3, and it comes from the coordinate
0 and 1.
0 and 1. There you have it. Okay? That's all there is to this. So again, where is the difficulty going to come in? The difficulty is going to be on reading and writing out your constraints. That's the part that's going to be tough. Other than that, this part should be easy. And you will be able to use some technology to do it, to help. You still need to know how to graph this on graph paper. This one should have been done on graph paper. Okay? So you have to remember how to graph using either y equals mx plus b or finding your x and y intercepts. You only need 2 coordinates, or you need 1 coordinate and a map to graph a line. Fair enough? Any questions so far about today? Okay, so that's all there is to it. And it just basically builds on what we did yesterday.